So it's time for us to get into drawing organic compounds and know that there are so many different versions of the way that we draw things. But I want to try to give you some examples, and definitely you absolutely need to practice this, as with everything in organic, but let's start with the basics, okay? So if we start with like the expanded structure or the Lewis structure, now notice that the Lewis dot structure would have dots in between atoms. So that bond, when it's just a line, we refer to that usually as the Lewis structure. Sometimes that's referred to as the expanded structure. These are going to list out all of the atoms that are there, including carbons and hydrogens, like all of this stuff would be part of the expanded structure. When we get to the condensed structure, we're now writing things as you would type them into like a typewriter. So we're going to condense so that the hydrogens, we put a 3 down there. And remember, that means that there's 3 of those hydrogens. So that would be the CH3 is from the one that is over here, right? And so the CH2 is in the middle, that's this guy, and then we have the CH3 over here. There's absolutely times when you can combine things, so we'll just have to work on that as we go along, okay? And then there's what's known as the line bond structure, or otherwise known as the Kekule version of the structure. When we go to this structure, all that we're doing is showing where the non-hydrogens are, unless it's attached to something that's not carbon. Well, I'll show you what I mean here in a minute. So when we do the Kekule structure, what we're saying is that everything that's the end of a line, like right there, that's a carbon. Anything where 2 lines meet at the vertex, that is a carbon. And then at the end of this line, that would be a carbon as well, because that's how you read these. Now, you might wonder, well, what happened to all the hydrogens? Well, first of all, when we get into much larger molecules, you're going to be thrilled that those hydrogens are gone. But what we have to realize is that carbon bonds 4 times. Just for what you need to know, yes, we're going to look at formal charges and how that can change, but you would indicate that. Carbon bonds 4 times. So if it's showing 1 bond right now, so right here, we've got this carbon right here. He's coming up to this one. So since he's got 1 bond shown right now, that means he has 3 hydrogens. This middle carbon has 2 bonds, right? 1 in each direction, which means that it's got 2 more bonds. That would mean that it has 2 hydrogen. And the same thing is true over here where it has 1 bond. That means that it would have 3 hydrogen. And that's sort of how we have to work through this. Again, practice makes perfect. Definitely want to practice these because that's how you start to realize what's really kind of going on. Okay, so that's what happens when you just have carbon and hydrogen. A lot of times we have what's known as heteroatoms, so non-carbon and hydrogen involvement. So that's what we have here on this second structure. We have an O and an H. Well, let's talk about this. Oxygen has 6 valence electrons. It bonds twice. But remember, it's got 2 lone pair on it. It doesn't matter if you're going to draw a line or anything to show a bond and you show oxygen, you need to show those lone pairs. As we keep going into mechanisms, as we get to the end of the semester, and when you get into Orgo 2, definitely you cannot survive without them. So let's just use that as a habit right now, okay? So when it comes to drawing these out, the OH took one of the spaces for the hydrogen, as you see from above, right? So that's sort of replacing the hydrogen from up here. But when we go to write this out, it's kind of the similar type of way. So we would say CH3 over here, then I would put CHOH, okay? Why? Because that's how we tend to write it. And you'll get a hang of that later. If you put COHH, is that wrong? We do tend to write it CAHOH, but that's something I think you'll get accustomed to over time more than anything else. And then at the end, we have another CH3. So how these two structures are going to differ is that you still have this same 3 carbons that we see here. So I would count that as in 1, 2, 3 carbons, just the same way that this has 1, 2, 3 carbons. But we also need to write in that OH. We might ask, why is it that we write that H in? Well, because anything that is attached to a non-carbon, including H, we write in. And that's just the way we do it. Okay? So next we're going to go to a more complex example. There's more carbons here. So I've got 1, 2, 3, 4, and then the 4th carbon has a CH3 going down this way and a CH3 going over this way. Okay? So when you start to write this out in the condensed structure and you keep getting bigger and bigger types of structures, we can start to sort of simplify things or condense things a little bit. So we would start by putting the CH3, and I'm going to read it from the left. So it would be CH3, and then notice that we have 2 CH2s in a row, right? So we have this one here, and we have this one here. So yes, you can write it out CH2, CH2, but over time that becomes easier just to write CH2 and then put parentheses around that, then say there's 2 of them. This guy would just be a CH, so that's where he comes from. And then we have 2 CH3s, okay? And so I've simplified that and put a subscript of 2 there. Sometimes it panics people when they first see a carbon that's by itself without an H. Yeah, that can absolutely happen as well. So don't let that panic you if it happens, okay? Now, I do recommend that you kind of number your carbons and make sure that everything is actually still there. So if we get over to this structure right here, we've got 1, 2, 3, 4, and it doesn't matter if you go up or down, 5, 6 carbons here. And over here we've got 1, 2, 3, 4, 5, 6 carbons here as well. Now, you may say, well, wait a second, your CH3 goes down over here and I drew it going up over here. Keep in mind, we are representing things in 2 dimensions. They don't even exist in 2 dimensions. Molecules are constantly moving, rotating, going all over the place. So those are the same. It's a matter of putting your hand out with your thumb down versus your hand out with your thumb up. It's the exact same thing. So either one of those is completely fine, and either one of those should be fine on an exam type of situation too. Okay. So let's keep going just a little bit more. Here we've got a CH3 followed by a CH2. And in this case, a carbon has a double bond to that oxygen right there, okay? And we note still that we've got 2 lone pairs around that oxygen, so we need to make sure we put that in, okay? So we would simplify this in the condensed structure as CH3, CH2, and then the C double bond O is just CO. And you might go, well, and then we finish that with CH3. So you may say, why is it? How do we know that that's going to be a double bond? Well, remember, carbon bonds 4 times, oxygen bonds twice. If there's no hydrogen there, the only way for carbon to get 4 bonds is to have 2 of them going to oxygen. Similarly, the way to get oxygen to have 2 bonds, it's got to have a double bond to that oxygen. Now again, it doesn't matter if you draw that C-double-O bond going downwards or upwards. Either one is completely fine. But you do need to have those lone pair of electrons in there. Okay? Great. Doing great. You want to give atoms as much possible room when you're drawing the Kekule form. So one of the things that we don't want to do, sorry about that, is we don't want to do something like this. That's a no-no, okay? Because you don't want to kind of just put all atoms in one area. Remember, Bonds are electrons. They want to be as far away from one another as possible. If you draw bonds, then you need to put in a lone pair of electrons. We were just talking about that, so I'm sure you got that down now. Okay. If you are having any issues, I would absolutely recommend that you work with a model kit, because model kits are so very valuable when it comes to being able to sort of see things and feel things and touch them in 3 dimensions. You know, we spend so long in our realities working in 2 dimensions because we're used to a piece of paper. But the reality is that that's not the tangible world. That's not the chemical world we live in, right? We live in a 3D world. So get your model kits out, construct that model, and you will see how things come together pretty easily, okay? So next we need to know what our different functional groups are. And yes, you've got to memorize these. And yes, I would suggest probably having flashcards or whatever it is that works for you. Flashcards don't work well for me. I instead prefer to have a list, which is why I made you a list. So let's go through these, and I'll go through these relatively quickly, but this is something that I would definitely suggest that, you watch videos on that have songs. I know of several that are songs or raps, or, make some type of art or something like that that is going to help you commit these to memory, okay? So alkanes just have single bonds, carbon and hydrogen. That's the simplest functional group that we get. Alkenes, notice that ends with E-N-E, is a double bond between 2 carbons. That's what those are. And they're harder to see in the condensed formula, but we can see them in the Kekuli form as a double bond. Alkynes, Y-N-E, is a triple bond between 2 carbons. Again, hard to see in the condensed formula. You'll get used to it. Here's a little pet peeve. That triple bond, there's actually a carbon right here. But keep in mind that this is sp hybridized, which means that this carbon has a linear arrangement, which is why this bond looks like it's the same as this, but those are 2 different bonds on 2 opposite sides of that carbon. So alkane, A-N-E is all single bonds, E-N-E is double bond, Y-N-E is triple bond. That does follow the alphabet, so that's easy to remember. Aromatics tend to be benzenes, and there's actually a whole field of aromatics, so we'll talk about that more, I believe in Orgo 2. Okay, so this has alternating single and double bonds. There's 6 carbons in here. We do not represent that as the condensed formula usually, although you can try to abbreviate that in a way that we'll talk about when we get there. And sometimes you see benzenes represented, like this specific type of aromatic, with single, double alternating bonds, or sometimes you see it with this circle on the inside, which we're going to talk about what that means in just a little bit. Okay, next we've got alcohols. There are multiple alcohols, not just a few that you might be familiar with. So alcohols have an O and an H, and that's connected to a carbon. So you can see that as OH there or an OH there. Notice their lone pairs are there. Carboxylic acids have an OH connected to a carbon, and on that same carbon, that's essential, it has to be the same carbon, there is a C-double-O bond right there. We call that an acid for a reason. You probably worked with this in general chemistry. There's 2 ways to write out the condensed structure. We can say COOH, or we could say CO2H. And here's how we would represent that. Next, we have aldehydes. So aldehydes are very similar to something called ketones, but aldehydes are all at the end. Get it? All at the end. At end, okay? So the aldehydes have a C double bond O with an H, and we would just say that's COH. Not to be confused with if you have like C CH, 2OH. That would be an alcohol. That's not what we have. We have COH. So what that's telling me is that I have a C connected to an O with an H here. Some of these you might need to draw out, especially if something gets more complex over on this side, to make sure that that's what an aldehyde is if you're given this condensed structure, because those are harder to see. Sometimes when it comes to the Kekuli, we will actually just draw the C double bond O like this. And sometimes you will see that H that's coming down here, even though we don't technically need it. So just be aware that those options can both be represented. Now a ketone is very similar to an aldehyde in that it has a C double O bond, but it's in the middle of a chain. It is not on the end. So that would just be a CO in the middle, and you can see what that kind of looks like. Next we have alkyl halide. So I put a chlorine here, but it could be any halogen. It could be chlorine, bromine, fluorine. It could even be, bromine, whatever you want, whatever you have there. So that would just be where one of those halogens is directly connected to that carbon, and you would put that in that structure as well. Make sure that you have your lone pairs. Okay, unlike alkyl halides, there's actually something called an acyl halide as well. And they sound and look a lot alike, so be aware that this is an acyl halide. Here we have a C that is connected to a double bond oxygen and a halogen. So both of them have a lot going on the end. They're going to have to be on the end because carbon only bonds 4 times. It's got 3 bonds that are occupied by the acyl halide, by the C double O bond, as well as the Cl. So it has to be sort of on the end of a chain, right? So we would see this as an acyl halide, and this would just be COCl. Notice all the lone pairs, we show them all. Okay. Next comes ethers. Ethers have an oxygen that are in the middle of a chain. So alcohols have an OH, where the O and the H would be at the end of a chain. Ethers are where you have an oxygen that's between carbons, so in the middle of that chain. So we can see that sort of here in the middle. Notice we again put the lone pair of electrons there. Ethers are again similar to an ester. Esters have a carbon that has a C double O bond as well as an oxygen in the middle of a chain. Remember, if we were to put a COOH, this is a carboxylic acid. Well, now we're replacing this hydrogen here with this CH3 or any other amount of carbons, and that is what makes it an ester. We can put the condensed formula in 2 different ways. We could say COOCH3 or we could say CO2CH3, kind of the similar way to what we did with carboxylic acids. Again, put your lone pair of electrons in there. Okay. Amines. Amines have a nitrogen, and nitrogen will bond 3 times, which means we got to show the lone pair of electrons that are there. Okay, now I represented this amine as having 2 hydrogens. It doesn't matter if it has hydrogens or if those are still connected to carbons. So in this case, it doesn't matter if it's at the end, if it's in the middle, or if it's sort of halfway in between. Amines are amines. It just means that there's something there with a nitrogen in it. And similar to amines is a functional group called the amides or amides. The difference here is that amides have a C double O bond that is connected directly to the carbon, or sorry, the C double O bond has the carbon that's involved in the C double O bond is also connected directly to the nitrogen. Oh, sorry, that was a lot to say. So we have this CO and H2 all grouped together there. And again, lots of lone pairs of electrons right there. Next, we have anhydrides. So as you would think, this would be without water, right? Anhydride means without water. And we'll show you why that's called an anhydride. I'm happy to show you now if you would like to know. But basically this anhydride is a C-O-O bond connected to another C-O-O bond through an oxygen. So it's CO2CO, and then whatever you have on each of those chains coming off of there. So it kind of looks like a little goalpost to me for some reason. Okay. Next, we have a thiol. So just like an alcohol, a thiol uses sulfur instead of oxygen, which sulfur is right beneath oxygen on the periodic table, so that kind of makes sense. So that's called a thiol. When we have an SH, we still need to have our lone pairs in there. And similar to an ether, we have an organic sulfide. Organic sulfide has a sulfur in the middle of two carbon somethings, and it doesn't have to be CH3, so those are obviously just examples. Okay, so we definitely want to put our lone pair in there as well. So that's a lot to take in, work on that, and see how far we can get.